Hello everyone, my name is Pooja and this is the demo for my project that is designing and comparing the performance of a 128 tap FIR filter, and now I'm going to demonstrate the second part of my project, that is integrating the FIR filter as a hardware accelerator on the FPGA board. So let's get started. This is my Qsys. I'm going to create a new project. Define it a directory called hardware demo. This is simply a folder. Name it as FIR, and the top level entity is FIR hard Qsys. Click next. No files yet to be added. Next, and these are the device settings that I need to do according to the board I'm using. So in my case, I'm using DE1 board, Alteras DE1 board, and for that these are the specifications that I need to specify. It varies from board to board. For simulation, I'm using models in Altera, and the formats of my files are, all my files are in Verilog. Next, and the project has been created. Let's launch Qsys and create our own system. Up to this, and most of the part of this demo is similar to that of the software part, apart for just one thing, and that is creating a new component in Qsys. So here we can see that we already have so many components in the component library that we can bring over here and create our own system. But in this case, we'll create a new component, that is our FIR filter in this case. Add the HDL files that define my system. So I have these Verilog files. These are all .v files that defines my FIR filter. So basically the FIR that I coded was this, and it instantiated these three modules. But in order to integrate my FIR with the Avelar interface, I need to create a wrapper or an interface to follow that Avelar protocol. So this is the interface for that, and I should define that as my top module. Now if you are using some different version of Quartus, this analyzing may not take automatically, so you just have to click the reanalyze HDL files and it automatically analyzes for any error or something. Over here I have to define the signal type of all the signals. This should be according to the protocols of the Avelar, and you can always change it according to the protocol that you are following. Read, and this is read data. Okay, so here there are three errors that says the interface must have an associated clock. So let's give it a clock and a reset. Oops. And it's all gone. So we are all set, and this is the name that appears on the component in this thing, in this part. So I mean, I can name it anything I want, but I'll name it the same, and I can specify that where should my component should be. So I can define my own group as well, or I'll just simply allot it to the special part, in special group, and finish. Yes. So if you go and see in the special, I have my component over here that we will ultimately bring over here. So let's create the system just as we did in the software part. A NIOS processor, simple one, on chip memory, and again I'll just to be on the safe side, I'll increase it to say 8K. I'll need a JTAG UART, It's all set. And of course a performance counter, and nothing to change. And last but not the least, our special component, and finish. The next thing is just give clock and reset to all the modules. Clock and the reset. The data master should go to all the slaves, and the instruction master should go to just the on-chip memory, because we are going to fetch instruction from on-chip memory. Now for the clock, we obviously need to give a clock from outside, and for this connection that we just made, we need to assign a pin, because this is the only IO pin that of the FPGA that we are using. So it's all set. Now we haven't assigned the base address, so now we have the base addresses, and let's save it. Yeah, I forgot one thing. In the NIOS, you have to say the reset vector and the exception vector. It's on chip memory and on chip memory. Finish. Okay, now we can save it. Here I'll give the same name as I gave for my top level entity. Make sure that this is the same, it is getting saved in the same directory. So it's saved, and now we'll generate it. This will take a bit longer. So basically the Qsys generates Verilog files for the system that we just created, and that will ultimately put in the Quartus and then burn it on the board. And generation is completed. We'll go to Quartus and import the file that defines our project in the Qsys synthesis. Over here, as I mentioned in the software as well, that there are two options. You can just import all these files and this file to your Quartus, or just bring one file, that is .qip file, and it will serve the purpose. Add, apply, and OK. So here it is. Now as I mentioned while we were doing in the Qsys, that this is the only pin that we used of the IO pin of the FPGA that we used. So we'll need to assign a pin address for that, pin assignment for that. So for this, now clock_clock is the name that the Verilog code we just generated from Qsys, that is in which we name it named clock as clock_clock. So we should follow that. For every pin we need to assign the location and the IO standard. In my board, that is Alteras DE1 board, location for clock is pin_L1 and the IO standard is 3.3 LVTTL, and just save it. Now we can compile our project. This again will take some time, and In the message window, we can obviously quick just ignore the warning, and the only thing that we should worry about is the error if something pops up. By this time, I'll get my board ready and attach it to my computer. The next thing we'll do is burn the system onto our board using the programmer, and the next thing is giving the burnt program the test bench. So let's wait for compilation. Here are the number of the percentage finished. I think this is the longest waiting time for the entire project. This one, the generation of the Qsys system. Okay, so the compilation is successful. Now we'll launch the programmer, and through the USB blaster in the mode as JTAG UART. Suppose let's delete this, and suppose there is no file, just add the SOF file. Make sure these things, the hardware setup and the mode, are correct, and your board is connected perfectly to the computer, and you see the fluctuating lights on there, and just start the burning process. The progress will show you the progress of your burning of this project onto your board, and even the lights on the board will stop fluctuating. So this is all set. Yes. And now we'll go to Tools and launch NIOS SPT for Eclipse. Here you need to define the workspace that you are working. So it should be the project directory that we defined. In our case, it's good to go. Okay. So over here we'll create a new project, a NIOS II application and BSD from template. It will ask us for an SOPC info file, so bring it from here. Every time you import a file, just make sure that you are in the corrected project directory. In our project, in our Qsys system, basically we define just one CPU, so it automatically gives the name of the CPU as the one. If you have multiple CPU, you will have more options over here, but in our case it's just one. Let's name this project as FIR NIOS, and I'm okay with the default location. And I'll select the hello world small, as it will go through lesser libraries and occupies less space. So just finish it, and it will create a project in my project explorer. And this is a simple code that prints hello from NIOS to the console window, and first we'll run that just to check the connection of our board and the system that we just created, or simply the computer and the board, and then we'll go ahead and replace it with our C code for FIR filter that will give it the test bench, that will serve as a test bench. So here the FIR hard NIOS is clean complete, and over here we'll just go ahead and build project. This again will take some time. So the project building is done. Now we'll run it as NIOS II hardware, and via this we expect that a hello from NIOS II. If you see this C code, it's basically printing a hello from NIOS II. So we'll expect that that in the console window we see this as printed. Oops, I think I forgot to didn't click it properly. This is just to check if our integration with the board is correct. Blinking, and see if the NIOS system says hello to us. Okay, so it's saying hello, and now simply in the space of this C code, I'll replace it with mine. Just delete it. I'm already coded the C code. So I'll simply copy it in my NIOS II, and to explain this is simply a C code wherein I am initiating the performance counter, giving it the values, printing few stuffs, and then giving the input values, the base address of my FIR interface. And one thing to make sure over here is the base address that we define over here. For example, in my case, the FIR1 interface, the base address of this is 5048, since I earlier did this, so I know that it's going to be this. So whatever base address is shown here should be there, and the same for the performance counter as well. It's 5000. So in my C code, the performance counter base should be 5000. So this is all good. Control S, just save it, and now we'll run this, and we'll expect the outcome just like the software part, and to see the output of the FIR and the number of cycle it takes. So run it as NIOS II hardware. It's all done. So I also printed this thing that in this part of my project I am using, this is simply a user peripheral that we are integrating to the Avalar system. In this case, we see the output of the FIR is -34, and the number of cycle it took was 31,999, which is pretty less than the one that we did with the software thing. So this is the end of the demo for my hardware part. You can compare the output, the number of cycles that is that it takes with the hardware part and the software part. So thank you for watching. I hope this helps.